Ever wonder how your GPS just knows the fastest route? Or how a video game character seems to know exactly what to do next? Well, it's definitely not magic. It's a special way of thinking, a process for taking a messy, real-world problem and turning it into a super clear step-by-step plan that a computer can actually understand and follow. So today, we're going to break down that exact process, the art of algorithmic thinking. So let me just ask you this straight up. How do you solve a problem? No, really, think about it for a sec. If you're trying to, I don't know, figure out the quickest way to get across town, or even just bake a cake, what's your process? Do you make a list? Do you just kind of wing it? We all have our own ways of doing things, but as you're about to see, the kind of problem you're up against, well, that changes everything. You see, problems usually fall into one of two camps. Over here, you've got your well-defined problems. Think of a simple math equation. There's a clear goal, a clear path, and one single right answer. But then you've got the ill-defined problems, like designing an entire sustainable city. The goal is massive, the options are practically endless, and there's no single correct solution. To get a computer to tackle either one of these, we need a solid plan. And for that, we need the right tools. And that plan? It comes from having a problem-solving toolkit. It's all about having a set of go-to strategies that you can pull out depending on the challenge. I mean, you wouldn't try to solve a crossword puzzle the same way you'd write a novel, right? Of course not. You need different tools for different jobs. Okay, so the most powerful tool in our entire kit is the algorithm. Now, at its heart, an algorithm is really just a step-by-step logical procedure. But, and this is the most important part, if you follow it exactly right, it guarantees you'll get a solution. It's like a foolproof map to get you from point A to point B every single time. The best way to think about it is this. An algorithm is just a recipe. Seriously, to bake a cake, you follow these very precise steps in a specific order. You gather the ingredients, preheat the oven, mix things together. If you follow that recipe perfectly, you are guaranteed to get a cake. It's the perfect, foolproof plan for a very specific result. But what if you don't need a perfect solution? Or maybe you just don't have time for a full, detailed recipe? Well, that's where our next tool comes in, the heuristic. Think of it as a mental shortcut or a rule of thumb. It's way faster and more flexible than an algorithm, but it doesn't promise a perfect outcome. It's for all those times when good enough is, good enough. Take a look at this maze. An algorithm would try to map out the entire thing just to find the single best path. But a heuristic, like backtracking, is so much simpler. You just start walking. You pick a path, and if you hit a dead end, no big deal. You just turn around and try another one. It might not be the absolute fastest way out, but it's a practical strategy that works without needing a perfect map before you even start. So we've got our toolkit of strategies. Now let's meet the magical tool that's going to execute our plans at, like, lightning speed. The computer. But here's the catch. We have to think of it less like a super genius and more like an incredibly fast and incredibly literal assistant. Let's get one thing straight. Computers are not smart. At all. They have zero actual intelligence. Their power comes from two things. They do exactly what we tell them to do, and they do it billions of times a second. All the cleverness, all the real problem solving, that still has to come from us. So how does it do what we tell it to? Well, it all boils down to this really simple three-step model. First, we give it some input. That's the data. Second, the computer will process that data based on our instructions. And third, it gives us the output, the result. Input, process, output. Literally everything a computer does follows this basic pattern. And if we could zoom way, way down into that process step, right into the computer's brain, you'd see this simple, endlessly repeating dance. It fetches an instruction, it decodes that instruction to figure out what it means, and then it executes it. Fetch, decode, execute. That 3-beat rhythm, happening billions of times a second, is the engine that drives the whole show. Okay, so we know the computer is a fast, literal assistant that just follows a simple cycle. But how do we actually give it the instructions? How do we write the magic spell that tells it exactly what to do? We do that with a programming language, and our tool of choice for this is going to be Python. We're picking Python because it's famous for being easy for beginners to learn. It's super expressive, which just means you can do a lot with only a little bit of code, and best of all, it's completely free. It's really the perfect place to start turning our ideas into actual instructions. Now, before we can work with any information in our code, we need a way to store it. And for that, we use variables. So right here, we're creating 3 of them. We're storing the number 10 in a variable we decided to call A, the text study glance goes into B, and a decimal number is getting stored in C. This is how we give our program a memory. Honestly, the absolute easiest way to think about a variable is just as a labeled box. That's it. You give the box a name, like A, and then you put something inside it, like the number 10. Then, anytime you need that number later on, you just call the box by its name. It's a really simple idea, but it's incredibly powerful for managing all of our data. All right, it is time. Let's put all these pieces together. We get what problems are, we have our strategies ready, and we know the basics of how to talk to our computer assistant. So let's take a real problem and go all the way to a working program. So here is our challenge, a simple 3-digit combination lock. We have no idea what the combination is. How can we use our brand new toolkit to crack this thing? What's the plan? We're going to pull a strategy from our toolkit called brute force, and the idea could not be simpler. We're just going to try every single possible combination, one by one, until that lock pops open. It's not clever, it's not fancy, but for a problem this size, it is absolutely guaranteed to work. So here's how that strategy turns into our algorithm, a recipe. Step 1, we start at the very beginning with 0, 0, 0. Step 2, we test it. Does the lock open? Step 3, if it doesn't, we just move on to the next number, 0, 0, 1, and we test that. We're just going to keep doing this over and over until it finally opens. That is our guaranteed recipe for success. And this right here, this is that exact algorithm translated into Python. This line here sets up a loop that's going to count through every single number from 0 to 999. That's our try the next number step. And this next line checks if our current guess matches the key. That's our test it step. As soon as it finds a match, it prints padlock opened and stops. This is the magic spell that makes our whole plan come to life. And that really just gets to the heart of it all. We didn't need some super intelligent machine to crack this lock. We just needed a machine that would follow our simple plan perfectly without asking any questions. The real power isn't in the computer. It's in our ability to create that clear, logical plan in the first place. And that whole journey, right there, is it. We started with a problem, the locked padlock. We chose a strategy, brute force. We defined a step-by-step algorithm, try every number in order. And finally, we wrote a program, our Python code. That entire process, from start to finish, is algorithmic thinking. So now you have the blueprint. You understand the whole journey, from a simple problem all the way to a working program. You know how to create the instructions that bring a solution to life. So the only real question left is, what are you going to build first?